Assalamu alaikum. I'm Mohammad Tariq Habibullah. Now I am going to give a presentation on Booth Multiplier. So what is Booth Multiplier? Simply we can say that Booth Multiplier is not a conventional multiplier. So why is it so different? What features make this multiplier other different from conventional multiplier, and how this multiplier works are the main topics of my presentation. Now I will describe in detail about these topics. So we know with the help of conventional multiplier only signed multiplication can be done, but with the help of Booth multiplier both unsigned and signed multiplication can be executed. So for a positive number and a negative number, the multiplication of those numbers can be done with the help of Booth multiplier. To the right, we see a picture of a gentleman, and the name of this gentleman is Andrew Donald Booth, and he is the designer and inventor of this multiplier. He is a British engineer, and the name of this special multiplier is named after him. Now there are some special features which make this multiplier different from conventional multipliers. Firstly, this multiplier has employed two's complement notation. Another feature, but the most important feature is the reduction of number of partial products. That means the number of partial product is less than in Booth multiplier is less than that in conventional multipliers. The number of partial products are reduced when multiplication are done through this multiplier, and this multiplier is faster than the conventional multiplier. So these two significant and extraordinary features make it different and special from conventional multiplier. Now, next, I proceeded to the architecture of Booth multiplier, and the architecture I will describe the architecture of Booth multiplier in concise through this flow chart and flow diagrams. At first, we have to input two binary numbers. These binary numbers may be positive or negative, and one of those binary numbers is a multiplier and another is a multiplicand. Booth encoder. The next block is Booth encoder, and this block assigns which operations need to be done on multiplicand. And the input of Booth encoder comes from the multiplier bits, and according to the multiplier bits, these Booth encoder assigns which operations needs to be done on multiplicand, and Booth decoder performs the operation on multiplicand according to the signal sent from Booth encoder, which indicates which operation needs to be done. After after performing the operations, we will send the we will we will obtain the 9-bit partial products. The next block is sign extend, and this sign extend block performs sign extension process. So why is this process necessary? We know the partial product that we obtain through Booth decoder consists of 9 bits, but in adder we need to input the numbers which consists of 12 bits. So to make a 9-bit partial products into 12 bits, sign extension process is necessary. And this adder sums up all the partial products produced from generated by Booth decoder and sign extend block. And after summing up all the partial products, then we will obtain final output, and final output is the final product of two input binary numbers. This is the architecture which is expressed in different way. And these are the Booth encoders, and the inputs of Booth encoder comes from the multiplier bits of x, bits of multiplier x, and this Booth encoder produce output of 3 bits, and these 3 bits indicate three operations. Three operations are multiplication by 1, multiplication by 2, and negating multiplicand. So these 3-bit output signals are sent to Booth decoder, and in input the 8 bits are also sent as the input of a Booth decoder, and the 8 bits belong to the multiplicand y. So using those two input signals, Booth decoder performs the operation on multiplicand. Then then we will obtain 9-bit partial products, and sign extend makes the 9-bit partial product to 12 bits, and the 12 bits numbers are sent to 12-bit adder, and 12-bit adder sums up all those partial products generated by Booth decoder and sign extend. And then these adder this is then after summing up all the partial products, we will obtain 16-bit output, which is the final product of x and y. Now I will focus on Booth encoder. So as I have stated earlier, Booth encoder assigns the performance assigns the operations which are required to be executed on multiplicand. These operations are single, double, and negate that I have stated earlier. This is the Booth encoder truth table, and the inputs of Booth encoder are x2i plus 1, x2i, and x2i minus 1. So these 3 bits come from the multiplier bits x. So in truth table we see that for for bit combination of 000, all the signals, all the output signals are disabled, have lower logic value. On the other hand, for a bit combination 111, single and double signals are 1, but negate signal is enabled. Actually, when x2i plus 1, when x2i plus 1 value has a logic value of 1, the negate signal will be enabled. But when regardless of x2i plus 1 value, when x2i and x2i minus 1 values are different, only single signal is enabled, but double signal is disabled. Here for 0 1 for 0 1 and 1 0 we will obtain single signal enabled. We see signal is enabled. Similarly, for 0 1 and 1 0, we see that single has logic value of 1. Next, but when the values when x to I and x to I minus 1 has different values, only double signal is enabled. For example, here for bit combination of 1 1, we see that double signal is enabled, but for bit combination of 0 0, we see that double signal is enabled, but single signal is disabled. And this is how boot encoder works, and this is how boot encoder selects the operation out of 3 operations. Next, I move to boot. I move into boot decoder. Boot decoder performs the task assigned by boot encoder. So we see when a single signal and double signal are disabled, it means that the multiplication the multiplicand will be multiplied by 0. So we will output, so the output will be 0. But when double signal is enabled, we that means that indicates the multiplication of multiplicand by 2. So multiplicand will be shifted by one bit to the left, and this is why pp will be equal to yz minus 1 when a double signal is enabled. But when a single signal is enabled, it indicates that the multiplication of y multiplication of multiplicand by 1, only 1. So the multiplicand will not be shifted by 1 bit to the left, like when it is multiplied by 2, when it is multiplied by 1. So when a single signal is enabled, the pp is equal to yz 0 0 0 0 1 1 1 1. So this is how multiplication by 1 and multiplication by 2 are executed through both decoder, and this can be confirmed by this truth table. This is the schematic design of boot decoder, which consists of 3 NAND gates and 1 XOR gates. So when a next signal is 0, this signal will not be inverted. But when next signal is 1, this signal coming from three NAND gates will be inverted. Then PPIZ will be at 2 1 when next signal is 1. Otherwise, PPIZ is not added to 0. Why next signal is that means the negative signal is 1, and the partial product, the bits of partial product is added to 1, because it's the mechanism of 2's complement, and this can be done through this boot decoder. This is a sign extension this is the truth table of a sign extend block. So when the 9th bit of partial product is 0, it's extended to a 3 bit by this way 0 0 1. But when a 9th bit of partial product is 1, the extended bits are 1 1 0. This is how 9-bit partial product are extended to 12 bits through this sign extension process, and this is the fundamental principle of a sign extend block, and this is how a sign extend block extends the partial products. according to the value, according to the bit of ninth bit, according to the ninth bit of partial product produced by generated by Booth Decoder. Next, we will discuss on adder, the last topic, and then I will show you example. How example? There are four adders which can be implemented in Booth multiplier. These are ripple carry adder, carry select adder, carry look ahead adder, cogstone adder. Out of those four adders, ripple carry adders is easier to design, but its delay is the greatest. On the other hand, conversely, cogstone adder is so complex to design, but its delay is least. It has least delay. It has the least delay. So, so it indicates that the complexity of structure of adder increases, the delay of the adder reduces. Moreover, carry select adder and carry look ahead adder is in the middle position according to the complexity of design and delay of the adder. So now I will show you an example. I will show you an example. So I will perform Booth multiplication between two numbers, -7 and 5. So the binary representation of 5 can be expressed in this way: 101 and 101, and but the binary representation of +7 is expressed in this way. This is the binary representation of +7 decimal number. Now we need to obtain the minus binary representation of -7, and we can obtain this by employing a 2's complement technique. At first, we invert all the bits of this number, these binary numbers, every bits. Then we will obtain this. Then I just add 1 to this binary number. Then we will obtain the 2's complement representation of +7, and this is the binary representation of -7. So to perform this multiplication, we assume 5 as a multiplier, and we assume -7 as multiplicand. So I have divided into 4 segments. I divided all the bits of multiplier 5 into 4 segments, and each segment consists of 3 bits. So how can I divide this? At first, for the first segment, the LSB is assumed 0. For all multiplier, we will assume the LSB of first segment as 0. Next, 1 0 comes from the first and second bit of multiplicand. Is from here, from this 1 0 1 0. Next, the second segment, the LSB will be at second bit, and MSB will be a fourth bit. 2 3 second bit, third bit, fourth bit. Yeah, second bit, third bit, fourth bit. 0 0 1 0 0 1 0. Similarly, the third segment will be fourth, fifth, sixth. 0 0 0 0 0 0 and 6 7 8 0 0 0. This is how I have divided the bits of multiplicand into 4 segments. Each of the segments consisting of 3 bits. So these 3 bits, these divided 3 bits are sent to the inputs of Booth decoder. So for 0 1 0, only signal is enabled. and this can be confirmed by the truth table of Booth encoder. 0 1 0, only single signal has a higher logic value, but all signal are disabled. Similarly, for 0 1 0, single signal is enabled only. And for all for 0 0 0 bit combination of 0 0 0, all signals are has zero logic value. All that means all signals are disabled. So all signals will be disabled. Next, the first operation is single. So single operation means the multiplication of multiplicand by +1. If negative signal is 1, then the multiplication of multiplicand will be by -1. But here, as only single signal is enabled, so we will perform multiplication of -7 by 1. So after that, we after performing multiplication by 1, we will obtain this number. We will obtain this number 1 0 0 1 0 0, then 5 1 1 0 0 5 1 1 1 1 1 1. So I have 8 bits. So ninth bit will be, and the ninth bit will be and equal to MSB of multiplier, MSB of multiplicand. So MSB of multiplicand is 1. So ninth bit will be 1. So for 1, for ninth bit 1, we will obtain the output of sign extend block is 1 1 0, B6 1, B7 1, B8 0. So this is B6, this is B7, this is B8. So 1 1 0, and to make it 12 bit, we insert 0 in front of this number. This is for the first. Actually, this sign extension truth table is effective for the first partial product. It's not effective, not use. It's not valid for second partial product. For second partial product, we will employ another technique. Similarly, will similarly the first 8 bit will be equal to the binary representation of -7 1 0 0, then 5 1 1 0 0 5 1. But next ninth bit will be 1. Nice, 9 bit will be 1, which is equal to the binary, which is equal to the MSB of multiplicand. Then this 1 will be, ninth bit will be inverted, and it will be inverted to 0. Then we will insert 1 in front of 0. Then to make it 12 bits, then we will insert 2 0. Similarly, when the -7, when we multiply -7 with 0, then we will obtain the first 8 bits 0 0 0 0 0 0 0 0 0. For the first 8 bit, it will be 0. But the second ninth bit will be 0, as 9 bit will be equal to the MSB of multiplicand. So the 9 bit 0 will be inverted to 1, will be inverted and turn into 1. Then we will insert 1. Then we will place 0 in front of this number. Similarly, we will this is the third partial product. Similarly, we will obtain the fourth partial product, which is equal to PP3 or third partial product. Now I will sum up all those partial products. This is the first partial product. Then we will place a second partial product under this first partial product, and say, and we will shift the second partial product uh, by 2 bits to the left of to the left with respect to the first partial product. Then third partial product is shifted by 2 bits to the left with respect to second partial product. Then fourth partial product is shifted by 2 bits to the left with respect to this partial product. So this is how sum is done. So here we assume 0. In this vacant place we will assume 0. This is how we sum 1 0 0 1 1 1 1 1 0. We have carry 1 1 1 0 and 1 1 11. We have carry 1, so 3 1 will be 11. So we have carry 1. This is how I have we got the final product of -5 -7 and 5. So the number that the number the final product that we have obtained, we should verify that is it equal to -35. We need to verify that. At first we invert all the bits, then we will add +1 to these 16-bit numbers. Then we will obtain these numbers, and this number is equal to +35. So this number is equal to this number is the binary representation of -35 and 2's complement of +35. So this is how a Booth algorithm works. And in Booth algorithm, we see that only 4 partial products are required. But in conventional multiplier, for multiplication of 2 8-bit numbers, we need 8 partial products. Here, the partial products number is reduced by half. So this is how the multiplication is done with the reduced number of partial products and faster process than conventional multiplier. So that's are the all things that I have described, that I have presented on Booth multiplier, that I have presented on Booth multiplier and Booth multiplication algorithm. So thanks everyone to listen to my presentation. Thanks everyone. I am now concluding my presentation, and thank you everyone to listen to me. Thanks again.